Record. Cool. All right. So welcome to lecture 4. This is one of my favorite videos from Dr. Sulman when we first started doing DeepRL, where he gets a humanoid to walk. It's sped up like 10,000x. But he's getting a humanoid to walk with this algorithm he calls TRPO. And that's kind of the basis of PPO and lots of the algorithms we use today. And so, yeah, look him up. Cool. But let's start with some logistics. Homework 1 we'll release on Wednesday. It's going to be on imitation learning. So we'll have imitation learning. Specifically, we'll cover behavior cloning, Dagger, and autoregressive policies. And we'll have extra credit being diffusion policies. I didn't go through diffusion policies in enough detail in class, but it's extra credit. So we'll send you some references and use ChatGPT if you want. But yeah, the goal of the extra credit problem is really to like give you an opportunity to implement something from scratch. And so we have 2 versions of the extra credit, one which is like more guided and one which is less guided. And so choose whichever one you want, doesn't matter. But yeah, that'll be imitation learning. You have like 2 weeks to do it. It should take a couple hours. But yeah, it should be fine. And please bother me or the TAs if you need more help on it. It's not supposed to be very hard. It's just meant to like concretize what we did in lecture. Okay. Some of you are not as familiar with PyTorch, so we're going to have a PyTorch tutorial on Wednesday in Jacob's office hours from 2 to 3:30. Sid, can you get the door? We'll have a PyTorch tutorial on Wednesday, 2 to 3:30, in Gate 287 down the hall. Feel free to skip it if you use PyTorch all the time. We'll release groups and papers for our seeded discussion that I discussed in our first class today, maybe by midnight or so. There'll be 3 groups presenting next Wednesday, so you'll have a little over a week. And the paper we're going to read is going to be, or I'll send them out. But basically, there'll be 3 groups, and we'll have 2 seeded papers. Pick whichever one you like best. And I'll send out a format of what we're expecting. And for everyone else who's not presenting, please read the paper so that it's a productive use of your time to have a discussion about it. Right? So you don't have to read the papers, but then you're going to be lost if you don't. Okay. And I'll release some sample project ideas on this Thursday. But let's plan to have people submit their project ideas by next week, maybe late next week, next Friday, so that we can there's some time for us to give you feedback. And so you can form groups of 1 to 2, and you just need to write like a 1/2 to 1 pager on what your project is going to be about. And it's meant for us to tell you if it's going to be like doable in time and if we have ideas on how you can build it. So don't worry about it being very formal or anything. Okay. Any other logistics that we should discuss? Questions? Okay, sweet. All right, so what we're going to talk about today is going to do a little recap. We largely talked about multimodality and imitation learning last time, plus a little bit of Dagger. So we'll recap that. Then we'll talk about like why Dagger can be kind of hard to implement in practice and some techniques that have been proposed recently to kind of address those. And we'll wrap up imitation with some frontiers. Then we'll start talking about reinforcement learning, specifically this technique called policy gradient. We'll derive the policy gradient, and then we'll talk about what makes the policy gradient challenging, depending on how fast we go. Sweet. Let's get started. So if you all remember, we talked about behavior cloning. It's simple, but it has these challenges. Specifically, it has 2 challenges, one of underfitting, where you're not able to fit the training data well enough, and the other one of compounding error, where your error grows quadratically with horizon, right? And so we started by thinking about underfitting, and we said, hey, underfitting is a problem when you have these bimodal distributions that you're trying to approximate with a Gaussian, and this kind of sends you to the middle, and you crash into like obstacles which were not in your training data, right? So really the problem of multimodality comes when you have your learning policy have lower modality than your thing that you're trying to learn or your data distribution. So your data distribution might be multimodal, but your learner might be unimodal, right? And so that's what causes problems like this. when you have mode averaging and so on. And so we said that, okay, multimodality is a problem. We can either deal with it by improving the expressivity of our distribution or by changing our objective, right? So our objective was this maximum likelihood objective. We're going to try changing that, or we can try changing the policy class to be better than a Gaussian. And so that's kind of what we covered most of last class. That try to follow that around? Yes. Okay. So the first thing we did is we tried to show that, hey, the maximum likelihood objective kind of boils down to something called the forward KL divergence, right? And we said the forward KL divergence is kind of what we do in behavior cloning, but it's one instance of a broader class of divergences, which are these F divergences, right? And we said that an F divergence is basically any divergence which is of the form expectation Q, F of P over Q, when different choice of F will lead to different divergences. And we said that forward KL, in this case, when you have your policy be a Gaussian, is going to lead to mode covering because you really don't want to miss anything in your data distribution. But if you choose F equal to minus log X, you'll get the reverse scale. And then the reverse scale leads to mode seeking, which means that you're just going to cover one of the modes and you'll be okay dropping the other one. And the intuition here, just to recap, is that in forward KL, the expert controls the data distribution that you're taking the expectation with respect to. And in reverse scale, the learner controls the data distribution that you're taking the expectation with respect to it. And so that's the primary difference here. Okay. And so we said, okay, reverse scale is great. But like, what's the issue with reverse scale? Does anyone remember?
We don't know pi theta.
We do know pi theta. You don't know pi e. Pi theta is the thing you're learning, right? So you don't know. So if you're trying to do pi theta versus pi e, right? You don't know pi e. So in the reverse scale, you're gonna have, oh, sorry. Your objective is going to be expectation pi theta log pi theta by pi e, right? Now the tricky part here is that you do not know the form of pi e, right? And the second tricky part is that you have to take samples from pi theta. Was someone going to say something?
No exploration.
So you have to do exploration, right? Yeah. So you have to do exploration, and you need to know what the expert is in analytical form. And so that's what makes reverse scale hard to implement. So while it doesn't have the issues of mode averaging, it has this issue of requiring a known expert, right? And it has the issue of requiring exploration. Okay. So that's the issue with reverse scale. What we're gonna talk about in the seeded paper discussion is a technique for making the reverse scale tractable. And so my former student Kay, she wrote a great paper about like how do we take reverse scale and make it so that you can approximate it without requiring a known expert just from samples. And so that's the paper we're going to seed for our discussion. I shared with all of you. But yeah, so to kind of improve behavior cloning, we either change our divergence from the forward KL to a different F divergence, or we use a richer distribution class, right? And so we said, okay, reverse scale is great. It's hard to approximate. Case paper gives us a path, but there's going to be some problems with it. The easiest thing to do is to just use a richer distribution class. And so we talked about a bunch of rich distribution classes, mixture of Gaussians, autoregressive policies, diffusion models. I won't go into those again, but that's kind of a recap of what we've done so far. Yes? Any questions? Anything that struck you over the weekend that we should discuss? Okay, good. So the second issue we've talked about is compounding error, right? So compounding error is basically saying you make a little mistake, you go a little out of distribution, make a bigger mistake, you make a bigger mistake, repeat, right? And so you're treating a sequential problem as a non-sequential problem, and that's going to lead to kind of a deviation between your training data and your policy that you get on execution. And so the main thing we talked about is to deal with compounding error. The intuition that you can follow is you kind of want to bring things back to the data distribution, right? Or you want to make the training data distribution as similar as possible to the policy data distribution, right? So if you have two different data distributions, one under your policy, one under your training data, you kind of want to make those as close to each other as possible. And so essentially all of the methods we're going to talk about, in some sense, try to bring P phi theta and P data as close together as possible. All right. So the first method we talked about was something called Dagger. And the idea behind Dagger is, can we make our training data, P data, as close as possible to the distribution you get when you execute your policy. So P pi theta over here is essentially what you get when you run your policy in the environment. P data is your training data, right? And so we're trying to say this is your offline training data, and this is your data that you get when you run the policy. You want to make these as similar to each other as possible, right? Because you're minimizing the difference between training and test at that point. And so the idea behind Dagger is just, can we try and make P data as similar to P5 data as possible, right? And you're going to do the like dumbest possible thing, which is you're going to say, you're going to train your policy from some human data. Okay? You're just going to do behavior cloning. You're going to run your policy in the environment, right? So you're going to train your data. You're going to have some data set. You're going to train. You're going to get a policy pi theta. Then you're going to run your policy in your environment to get some data set of observations, right? These observations need not be optimal. They're just what you're going to get under your policy. And when you get these observations, you're then going to ask a human to take each of these observations, which may not have been optimal, and then label them with the optimal action, right? Or whatever they think is optimal. And then you're going to like have a new data set now with actions labeled, right? With like optimal actions labeled or close to optimal actions labeled. You're then going to take this data set, you're going to aggregate it with your previous training data set, you're going to repeat, right? And so it's called Dagger data set aggregation, because literally just aggregating your data set. You're like taking your data, training a policy, running your policy in the environment, using the human to label optimal actions, taking that data set now with optimal state or optimal actions for the states that the policy visited, adding it back into your data set, repeating. Right? And so what you can see here is that essentially this thingy is P pi theta, right? It's what you're getting from running the policy in the environment. And this thing is P data, but what you're doing is you're kind of mixing together P pi theta and P data. You're taking P pi theta, labeling it with optimal actions and mixing it into P data. And so the hope is that as you keep doing this, like essentially, here's a way to think about it intuitively. Let's say this was your training trajectory. You like had some compounding error, you reached here. Now in each of these states, the human is going to label something that is optimal. Now your training data is this whole thing, right? So you no longer make the same mistakes out over here. You'll maybe make mistakes over here now, but that'll again be added to the training data, right? And so you're going to essentially keep increasing your training data. And so, but the important thing is you're not just increasing your training data on arbitrary states, you're increasing your training data on the states where the policy is failing. Yeah.
It's sort of like what reverse scale requires.
Yeah, it's very similar to what reverse scale does. Yeah. In some sense, you can kind of think of the human expert as kind of like your log pi e, and it's saying that I'm going to run P pi theta and I'm going to label it with log pi e. That's very similar. Great observation. Sorry. Okay. Great. Now, for some reason, my screen refuses to erase. Yeah, I guess we'll keep going. Okay, so does that make sense for a dagger as a principle? Okay, so the key idea, remember, in Dagger is that you're going to keep aggregating your data set, but not arbitrarily. It's not like I will just collect more data. It's like I will collect data in targeted places where the policy is making mistakes, right? So the difference between collect more data and doing Dagger is that you have to do it in the loop, whereas if I just collect more data, I'll just collect more data offline. Whereas when you're doing Dagger, you have to train your policy, you have to run your policy to see which states you're going to get the data, which states you're going to get the human to label, right? And so it's not just collecting more data, it's you're collecting labels on the data where the policy is failing. Right? So it's like kind of like targeted data collection. Okay, so that's the idea of Dagger. Does anyone remember what's wrong with it? Like what makes this hard to apply to real systems? Yeah. Yes. Yes, right. So it's expensive because the human needs to label the data. And the second is the same issue that we had with reverse scale, right? We have to like run the policy in order to see where we fail. And if we had to run the policy, then you like need access to the environment, which is expensive and maybe unsafe, especially when your policy is making mistakes. Right? Like I don't want an autonomous car to go crash, and then I'm like, I could fix it now. And so, yeah, so that's what's going to make it hard, right? That's kind of a recap, right? So what we talked about is multimodality, Dagger. Dagger is a reasonable algorithm, but it has this burden of getting a human to label. Actually, there's three issues. One is that a human has to label. The second is you need environment access, right? So you need environment access, meaning you have to have the human label, you need to have environment access, and you need to do this like after the fact. And so you have to like see what states you got to, and then a human has to go back and label them. Like if I was doing it for a simple system like a car, maybe, or like a easy to control system like a car, maybe. But if I'm doing it for a like bimanual manipulator, it's not obvious what the optimal actions would be or how I would provide them, right? And so that's what makes it hard to apply here. Okay, give me a second, guys. So I need to get rid of this, otherwise it's gonna be there the whole time. Okay, I guess we have to live with this line now. Sorry. Okay, so we talked about the pitfalls of Dagger. That makes sense. We're gonna try and address the pitfalls of Dagger. So we're gonna talk about two things. One of the things is how do we get away without requiring data collection in the loop, right? How do we do it without requiring humans to be there all the time? How do we do it without requiring us to run the policy all the time in the environment? And the second is how do we get away without this burden of expensive human data collection? And so we want to make Dagger cheaper. What are ideas? How would you make Dagger better? Now, if you were to reinvent Dagger in 2024, how would we improve it?
Use simulator.
Use a simulator. Yeah, it's a good idea. The problem is then you have to make the simulator.
I mean, yeah, you can borrow a very good simulator from someone else.
Yeah, you could.
But you don't have
You
to.
could. The tricky part with the simulator is that you have to get the simulator to match the real world. And so it's not that I just need a simulator of an arbitrary scene. I need a simulator of this scene, and I need to estimate the state for this scene. And so you need to solve state estimation, which is pain. But it's a reasonable idea, and we're going to kind of do something like that. Other ideas? Yeah.
If you have a human labeling the model running in real time, then would that reduce the safety?
Yes, exactly. So that's the first thing we're going to do. Basically having a human more involved in the training process. Or the data collection process, rather. Okay, so the first thing we're going to do is we're going to say, rather than doing this thing where we go collect data and label things after the fact, what we're going to do is we're going to collect noisy data at training time, right? And so the idea is rather than like collecting noise-free data at training time and then like going after the fact and labeling things, what we're going to do is at training time, we're going to add a bit of noise into the system, right? So this figure says that if you're starting here, you want to get there, like a noise-free path will go right through the middle, right? Instead, what we're going to do is we're going to add a bit of noise to the data collection process itself. So like the human, let's say, said go this way, you're going to add a bit of noise and go that way instead. And so it's like a little frustrating for the user, but in the process of doing that, what the human has to do is they like essentially correct your system, right? And so it's like, if you ever control any system with jitter, you like learn how to like compensate for the jitter. And so what that eventually ends up doing is that you add a bit of noise, and that noise kind of brings you to these states. And then the human naturally will like correct and compensate for that noise. So it's like over here, it'll kind of bring you back, right? And so at training time, what that kind of lets you do is rather than just collecting data for a single state, you kind of collect data for like a tube around the optimal data, right? Which means that like under some continuity and smoothness assumptions, if you like deviate from here, you're gonna like still have data coverage because the human kind of brought you back, right? And so all that this means in practice is that we're just going to collect data with a bit of noise at training time, right? So if you're ever running behavior cloning, Good tip is just add a little bit of noise into your data collection at training time. And noise means the following, that it doesn't mean that you store noisy actions, or it doesn't mean you like store fake actions. So like if I'm at state S, right, the human commanded, let's say action A. Instead of executing action A in the environment, you execute action A plus epsilon, right, where epsilon is noise. So the human wanted you to go here. You're instead going to do this, and then you're going to record S comma A plus epsilon, right? But the human is just going to like end up bringing you back. So you're going to get like data coverage around the optimum. So the key idea here is just you're going to collect data with a bit of noise during your training time, and that's going to help a lot at test time.
Do you add the S comma A plus epsilon to your data set, to your training data set, or do you ignore the actions that led you to the slightly?
You just add S comma A plus epsilon to your training data set. You ignore A. Like basically A doesn't exist to the learning system, only A plus epsilon exists.
So now the learning system is like.
Learning, it's almost like data augmentation. You have to like learn to deal with the noise, right? So remember, just add a bit of noise to your data collection and let the human compensate. And so there's like a nice set of formalism you can come up with here. For instance, you can like think of this as like maximizing likelihood, but you're just adding noise according to noise distribution. And there's a nice theory which talks about how much noise to add. But essentially, it just boils down to add noise at data collection time, which is like what works across lots of machine learning, just data augmentation. Yes.
For categorical actions,
Mhm.
how do you do that?
Yeah, that's a great question. So what you would probably do then is you would resample with some likelihood. You do something like epsilon greedy, which is like resample with some likelihood from the categorical distribution.
Yeah.
But yeah, the smoothness doesn't hold, so you can't add noise the same way.
Just to clarify, is this happening as during the initial data collection?
Initial data collection. So
after the model has already done.
So when you do this kind of thing, you don't do repeated data collection and training like Dagger. You just collect more data at training time. So this, I mean, you can always pair this with Dagger, of course, but this is saying that it's just like every time you collect data with a human, you're going to collect data with noise. Okay. Would you guys be okay if I like got rid of the scribbles on my screen? And okay, great. I might have to. Normally they go away, but not today. Okay. Aha, great. It's solved. Right. Sorry. Okay. So the main point here is you're going to collect data with a bit of noise. The human is going to come and help fix your noisy issue. And that's going to let you solve longer horizon tasks. And it's essentially, there's a lot of theory around this. If you want to look for things, look for Cube MPC, right? This paper is called DART. But generally, there's like a big set of theory around tube MPC and how you can collect a tube around the optimal policy, and that stabilizes you. Okay. The issue with this is that in certain scenarios, you can't actually afford to have noise. Right? So imagine that you're doing robotic surgery or you're doing like precision manufacturing. Like I can't have my robot like jittering. It's like not acceptable for data collection just because of the precision requirements of your problem. And so while it's okay in certain scenarios, in other scenarios, it's not acceptable to have noise during data collection, right? And so what happens is instead it's like here they were trying to do like manipulation with chopsticks. Like imagine you were trying to do that with noise added to your, data collection problem. It's pretty hard to do. It's hard to do already, but if you have noise, but this is not always possible. Okay. Now, kind of with this thing in mind of like, it's not always possible to add noise. and it's not always possible to have human demonstrators be in the loop. A couple of our students started thinking about how do we kind of avoid having humans in the loop? How do we avoid online data collection? How do we avoid having to deal with noise, right? And so their key insight was, how do I generate data synthetically to be corrective for imitation learning, right? So instead of saying, we're going to have a human provide those labels, or we're going to have a simulator provide those labels, they were, well, it's in some sense a simulator, but instead of having like a physics simulator provide those labels, they were trying to think of how can we use learning-based methods to synthesize corrective labels for imitation learning. And so the key point is I want to operate under the same assumptions as behavior cloning, right? So all the methods we've talked about so far operate under different assumptions than behavior cloning. For instance, Dagger needs you to collect data in the loop, have a human labeling things. The method we talked about just now, Dart, requires you to have a human deal with noise during the data collection process, right? And so they're operating under different assumptions than behavior cloning. So you have to like either change the data collection process or have an iterative loop or have a human expert come in, label things post hoc. And so what Kei, Yunchu, and Abe were thinking about is how do I operate under the same assumptions as behavior cloning? So I'm just going to get a data set, but I still want to get this corrective behavior to deal with compounding error, right? Does that make sense? Like, you don't want to like assume extra things about your environment or put more burden on the human, right? And so their question was, how do we find corrective labels for imitation learning without requiring humans in the loop or without requiring them to deal with noise in these kinds of precision applications? So their idea here was super easy. It was basically saying that if you knew the dynamics of your environment, right? So like Sid was saying, if you knew a simulator or something that looks like the dynamics of your environment, which says, if you're at ST, you took action AT, you got to ST plus 1, then you can synthesize corrective labels by just saying, let me find states ST and actions AT such that states ST and action AT will project it through the dynamics of your system, bring you back to a optimal state, right? And so an easy way to think about this is that if I knew how the world worked, if I knew the dynamics of the world, I can try and find a state and an action which will bring me back to an optimal state, right? So I can like synthesize a bunch of data that looks like this, right? By just finding states and actions, which when projected through the dynamics, give me back optimal states. Okay. Does that make sense? So the point is that the dynamics tell me how the world works. That says that if I'm at state ST, I took action AT, it tells me what state ST plus 1 I'm going to get to, right? That's what the dynamics tell me. It's like, if I was here, I push this, it would go here, right? And what you're trying to do is you're trying to find states ST and actions AT, which go to some states ST plus 1, which are really close to the optimal states. And if I can find these things that are close to the optimal states, then essentially I like go back to the training distribution. Right? So the training distribution is ST plus 1 star. I'm trying to find S's and A's, which in one step will bring me back to the training distribution. So notably, S's and A's are not necessarily in the training distribution. S's and A's are just things that bring me back to the training distribution. Yeah. And so S, for instance, can be an OOD state, right? And it's just saying that from S, if I take A, then I go back in distribution. So you're just going back. Think of it as like lines going back to your training distribution. Yes.
Synchronization speak over S. What I understand is if you are at a certain state, then you want to find that action. So the minimization will be over just the action.
Yeah. So here what's happening is that all you know is this optimal data, right? This thing in the dark line. What you're trying, and you don't even know what the out of distribution states are. So what it's trying to do is both find the out of distribution states and the actions from those out of distribution states that are bringing you back to the data. So essentially, it's trying to do like a one-step look ahead and saying that like, find me both the states and the actions that will come back to the training data. Right. So if I knew what ST was, then I would say, okay, take a particular AT. But here I'm saying I don't even know what ST is. Find me all the possible out of distribution states, which in one step can bring me back to the trading data. Right? Okay, does that make sense? Yeah.
So S T plus 1 star is like not a particular state that
Yeah.
is in distribution.
Yeah. We do this over all states.
But it still work if you're more than one step away from being.
So then what you have to do is you'd have to find ST, AT, ST plus 1, AT plus 1, blah, blah, blah. So that ST plus K star is close to F of, F of, F of, F of. So you have to do like a multi-step look ahead in that case. This is a one-step look ahead. What you're saying makes sense, but it has to just be a multi-step look ahead. Yeah. So the easiest way to think about this is just like something that brings you back to the training distribution, trying to find states and actions that bring you back to the training distribution, but they might be not in the training distribution. Yeah.
Give a physical example of the same action that will bring you back to distribution.
So let's say your arm has been taught to pick things up like this, right? The state might be a little bit to the left, and action might be a corrective action back to the right. Right? So it's like, let's say it's my robot arm. It's like, this is my target. This is what I've been taught, right? And like an out of distribution state might be the arm in like an out of distribution position, like a slightly different position from what I've seen. And the corrective action might be like, move the arm more to the right so you can get back to things that you know. Right? And so, like, does that make sense? Okay. Yes. So I guess what we do in practice is we just solve for k different things, and you just add those to your data set. So you just sample. Yeah. But I guess the premise there is that you're not trying to include all possible S's and A's. You just want to be better than your initial training data.
I missed a step at the start. How do you get that?
Yeah, I'll get to that in a second. This is assuming you knew F.
We always, so if you are like multiple steps away from in distribution.
Yeah.
Do you take one step that gets you as close to the distribution as possible? And another step that gets you as.
Yeah, that's a good question. I guess so. The way we're going to do this in practice often is that we're going to reject anything where this epsilon is too big. And so you're not just going to choose anything that is like as close as possible. Here, we're just going to choose things that are close, like in one step. And the reason to do that is we're going to talk about this in a second, but F will be a learned thing. And then the like error in your learn thing will get more and more and more as we increase the horizon of search. And so maybe let me get through the next slide and that'll be more. Let me get through the next slide. Maybe this will just so we have full context, right? Okay. So if we knew the dynamics, we would solve an equation like this. This would give us some S's and A's. We take those S's and A's, we add it to our training data set, but the assumptions were kind of the same as behavior cloning, except you assuming that you know the dynamics, right? And so the intuition is you want to find states and labels that bring you back from an out of distribution state back to an in distribution state. You add those to your data set. So your data set goes from being something that looks like this to like something that has like coverage over some region around it, right? So this kind of like augments your data, but it's not just like random augmentation, it's augmentation according to the dynamics of your system, which bring you back to the data. The problem that someone brought up was that you don't know the models, right? F is unknown. Like if we knew F, we could do lots of other things. So F is unknown. So we want to do this kind of intuition, but we want to do it under the assumptions of behavior cloning, which does not know F, right? So how do we do that? Well, we're going to use machine learning again, right? We're going to say, let's try to learn an F. Right? And so we'll cover this in detail in the model-based RL lecture, but the idea here is let's try to learn an F, which is like as close as possible to the true dynamics of your system, right? So we're just going to collect pairs of ST, AT, ST plus 1, and we'll collect a bunch of these pairs. We'll try and learn a model that takes in ST, AT and predicts ST plus 1, right? So it's like a dynamics model, something that takes in states and actions and predicts what the next state would be. And you try to learn this from your behavior cloning data. So your behavior cloning data is essentially ST, AT, ST plus 1, ST, AT, ST plus 1, right? So far, we've just been trying to learn policies. We can also use the behavior cloning data to learn a dynamics model. So something that takes in ST and AT and predicts ST plus 1. Yeah. And so we're going to try and learn a model which tries to predict ST plus 1 as accurately as possible, but just on the data that you use for behavior cloning. Right? So what this is going to be an approximate F, right? So we don't know F, but we're going to try and learn our F from the data that we got. Right? It's the same behavior cloning data. So now what we have is we have an approximate F, and we're going to take our same equation to find the S's and A's, and we're just going to stick an F hat into it. Right? So all we're going to do is we're going to say we're going to approximate our F using learning. We're going to stick in F hat in place of F, and we're going to say find the S's and A's, which bring me as close to the training distribution as possible. Right? So what's the issue with this? Yeah.
Kind of know the answer, but you can't trust your dynamics model everywhere.
You can't trust your dynamics model everywhere, right? So your learned dynamics model F hat is only accurate around the is only accurate in certain places, right? And so you can't really trust this to be solved everywhere. And so what we're going to do is we're going to do two things. One of the things is we're going to impose some smoothness constraints onto your dynamics model. So you're going to say, hey, dynamics model, you can't just make arbitrarily large changes. You have to be smooth, right? So you have to say small change in input can only change the output by a small amount, right? And that's something you call your Lipschitz constant of your function. So you're going to say that you want to pick F hats, which have a small Lipschitz constant, which means they don't change a lot. Okay? And if they don't change a lot, then they can be trusted in some region around the training data. So the point here is that we want to get back to the training data. We got F hats. F hats are not great everywhere, but if they're smooth, they can be trusted in some region around the training data. Right? So the first thing we want to say is let's learn smooth dynamics. And then the second thing is we're going to only solve this equation in regions where the dynamics model can be trusted, right? And so we're going to say, let's not get labels everywhere. Let's only collect labels in the regions where the dynamics model can be trusted. And so you solve an objective like this, which says, find the corrected label using F hat, but only do it in things that are close to the training data, right? And so you're going to say, let me find things that I'm not going to generate a corrective label that goes all the way from here back to here because I can't trust my dynamics model. So I'm just going to do this. I'm going to solve this equation, but I'm make sure I only solve it in regions where I'm close to the training data.
Is that smoothness or trustworthiness a property of the world you're saying, or a property of the model?
It has to be a property of both. Right.
So how do you know if it actually works? Because this comes up in neural engineering where you're stimulating the brain and it's a chaotic system. How do you actually measure if your model is going to hold slightly?
So for F hat, you can measure it because you know the functional form. Right? So you know the functional form, so you can perturb the input and you can see what the output is. And the way that you enforce F hat for the learner is that you impose things like spectral norm regularization, which is essentially trying to minimize the largest eigenvalue of your matrices. What that's going to do is not let your function be very non-smooth. And so in practice, you're just going to impose spectral norm regularization onto F for the learner. Now we can talk about whether it's true for the world, which is harder to do because you don't have access to it. The only way to really figure out is empirically, you collect more data there. And so I guess what we found is that for many robotics problems, large parts of the space do have smoothness and some parts of it don't. And so for instance, on the moment of contact, you're not smooth, but for large parts of the motion, you are smooth. And so you kind of that's largely an empirical question. But yeah, it's good. Because if you knew the model, then you would know it, but you don't. And so you only have data from the system.
So I guess a follow-up question then is, how do you actually detect when it's not?
Yeah. The only thing you know about the model is data from the model, right? So you only know that at some state ST, if I took action AT, it took me to ST plus 1. And at some state ST plus epsilon, if I took action AT, it took me to ST plus 1 prime, right? And you can say that, okay, if these two are pretty close and these are pretty far in the real world, right? Not in the model, then you know that there's been some non-smoothness, right? And so the way that you often do this in practice is that you can learn a super expressive model And then you can see in which places in those models was there like a big change in the true system. Yeah. Okay. Yeah.
So after you learn your dynamics model, how do you solve the optimization problems find ST and AT?
Yeah, in this case, we use this like backwards Euler optimization. So you just use the gradients to the dynamics model because you know it. But you could just do it with sampling. You could do it if your model is convex, you can do it with some convex optimization. You can do it with gradient descent. Like it's an approximate thing anyways. And so the way we do it is we like you solve with this backward Euler thing, and then you reject samples that are like not within these constraints. I missed one of your questions.
Yes, but I think it was, is it, did this occur as an idea where you want to figure out whether that or interested for some state? You have like access to a simulator that's not great, but like it is like good enough.
Yep.
And like you can't be worse than the approximate simulator, like, or if you're like you could.
So it
use
gives
that
you
as a
some lower
sanity.
bound or something?
Yeah, something like a sanity check.
Yeah, I mean, at least you can reject those parts, right? Like you could say, I'm not, I like, if the lower bound is non-smooth, then it's like, this is not going to be any better. Yeah, that makes sense. Yeah.
There's a more practical question. Is F does F take a lot of resources to train?
So in practice, what we did is we trained things mostly from low dimensional state, not from perception. And so the models are still pretty small. If you had to do it from perception, lots of things get more complicated. Like what does smoothness mean from perception? How do we train models efficiently enough? Like those things become problematic. So the important thing to remember here is we're not actually going to use this at test time. We're only going to do this at training time. So you're going to take the data, you're going to train the model, you're going to solve this optimization at training time. And then you're just going to learn a policy, like plain old policy. So at test time, it's fast. It's just slower at training time. So it's slower training time, but it's still hard from perception. So like we haven't applied this to perception. But yeah, it would be harder.
Has anyone tried it?
No, you should. That'd be good. No, it's a thing that we've been meaning to do, but we haven't done. Okay, so some cool videos. We set up a little piggy bank task. If you have like no corrective labels, you'll see that sometimes you like end up drifting from your path and like missing, in this case, missing the insertion, I think. Oh no. Oh no, that's the with corrective labels. Oh, good, good. Oh, working too well. And then without corrective labels, you'll see that it tends to like drift off and miss the target. Remind me of your name?
Oh, I'm Rico.
Rico. Yeah, so you can see, Rico, that if you like look carefully at this video, there's like a little marker on the coin, which we track. And so that's how you get the position of the coin. So it like looks like you're not tracking it, but you are. And so whenever you see robotics videos, they're like mostly fraudulent. So like look for these things, you know. Okay. So you can kind of like apply this to a bunch of different tasks, and you'll see like a marked difference between things with and without corrected labels. Especially when you introduce disturbances into your system. Like let's say someone goes and pushes the arm, it doesn't recover, whereas with corrected labels, it does. Okay. So yeah, like yeah, go ahead.
Is had more like predicting things compared to
Yeah, because I guess the bet here is that the complexity of how to solve a task, like a phi theta is kind of connect state to action. And it's not clear whether the connection between state and action has smoothness properties. Whereas when you're kind of like, in most robotics problems, there's like some continuity and some smoothness in your space, because you're like using the geometric space. And so it's easy, like at least empirically, we found that it's easier for us to impose continuity things onto the model while still having a complex policy, while it's not clear if you like put smoothness things onto the policy, whether it's still able to solve the task. And so basically, like if you make the policy smooth, like your point is that if I go out of distribution, a smooth policy should also not freak out, right? I think that basically like policy state to action relationships are more complicated than state to state relationship. That's the thing, which is largely an empirical. And then the second thing is that, like if you're doing data augmentation, you're at least letting your learner continue to learn from the optimal data. Whereas if you're restricting your policy class, you're like restricting how well it can learn from the original optimal data. And so you're like losing something. Yeah, but yeah, some of these are unsatisfying because this is like recent research work, and so there's like open questions. Okay, good. So some open questions in imitation learning. We've talked about everything under the Markov property. The world is not Markov all the time, especially human demonstrators are not Markov. So like, for instance, if you ever demonstrate something, you'll often like pause. You will try something again, you pause. And if you pause, that's non-Markovian, right? Because you're doing different things at the same state. And so you might need to have recurrent policies or things to deal with that. It's not clear that these things generalize. So like, for instance, if you train on the left, it's not clear that it generalizes to the right. It's not clear how to train this from action-free data right now. You train it from these expensive data sets that you collect on a robot, which takes a lot of human effort. And so you want to learn from like ideally YouTube videos or things like that. It's not clear how to do that yet. It's not obvious what data is good data, right? So it's like if I'm trying to collect data for imitation learning, it's a bit of a art. Like those who've done imitation learning a bunch know what data is good and what data is bad, but it's not codified formally. It's hard to deal with embodiment shit. So for instance, you're collecting data with a human hand. How do I make a robot do it? It's not obvious. And then lastly, there's like a bunch of work on better teleoperation interfaces. Like this one is called the UMI. So it's basically trying to make teleoperation easier. So rather than having to control thing with a puppeting interface or anything, you just wear these little gloves, and then you can transfer things to a robot directly. So those are kind of things that people have been thinking about for education. This is one of Jaffe's papers that I thought was cool, but it's basically on learning to retry. And when you have imitation learning right now, if it fails, it fails, right? And it's also useful to think about imitation learning not just as a zero-shot method, but how do I get imitation learning to keep improving? So if I like fail, I don't just give up and say I failed. How do I try something better the next time, right? And so his work is kind of a start at it, but I think there's like lots of interesting things in that space. Cool. And send some cool videos. This is from 1X. This is like last year. I think they have a better video out this year. But this is all trained with just behavior cloning plus tricks. So just imitation learning. And this is autonomous, which is pretty neat. I think they're actually deploying in homes now. This is another one called Mobile Aloha. Maybe so you've seen this. But it's again autonomous with imitation learning. The nice thing about it is that you can like apply to deformable objects and liquids and so on, because you're not assuming anything about known state. You're just using data collected in the environment. And lastly, this is one from TRI where they're doing diffusion policies, which we talked about in class. And they're using it for like all sorts of like dexterous kitchen manipulation tasks with precision and force application and so on. So arguably, imitation learning has been working quite well for robotics. I don't think it's at the level we can trustworthily deploy it in the real world yet, without oversight, but it's really working quite well. So it's promising to look into. Okay, so some perspectives here are that behavior cloning is nice because you can just collect some data and run it through supervised learning. Often it can be unreasonably effective, as in it just like works. But yeah, really what makes it appealing is ease of use. The cons here is that you have these issues, compounding error, multimodality, not clear that it really generalizes, and it requires this expensive data collection. So a lot of the demos you will see have like tons of data collected in an environment, and they don't really talk about the cost of that data collection. And so where reinforcement learning and things are helpful is to kind of deal with these types of errors, these types of issues. Okay. Questions before we keep moving? How do we feel about imitation learning? Good. Yeah.
So it's like imitation learning is trying to get the robot to the same problem as the expert.
Not in the same setting. It's trying to learn a policy so that you can do it in a different setting. The problem is that it's not clear that it works in really different settings. it works with some perturbation on the initial state, but it's not clear that it really got the intent of the problem and can really generalize. So something we'll cover later on is inverse RL, which is supposed to generalize better, but it's meant to work in difference.
More of a general, are the noise inherent with the system a big obstacle to our internet working, or is it more the problem of our policy?
You mean in the hardware?
Yeah.
In my experience, like especially in like the last 3 years, the hardware is getting much more reliable and much more consistent. And so there's some noise, but it's not like an impediment to the policy typically. Like the noise is within the range of things that the policy can handle. What I think is like, so for instance, you like run the same thing again. If you deal with compounding error, then like with any of the techniques we covered, then I think you can repeat in the same scenario. You show it a new scenario, that's when it starts to struggle. And so I think it's not quite the noise of the system, it's more the distribution of scenarios for your policy. Cool. All righty. That's imitation learning. What are some good resources? Oh, actually, there was recently a tutorial at RSS by Russ Dedrick and Laryl. Anyone who's interested in imitation learning, go look at it. It's a great resource. It's like a full day tutorial, so it has like tons of detail. Okay, so should we move to reinforcement learning? Sweet. Okay, so we have now covered imitation learning. We're going to start by thinking about policy gradient. How many folks know what policy gradient is? Good. Okay, not that many. Otherwise we could skip the whole lecture. So if you remember the objective of reinforcement learning, we want to learn a policy that maximizes the expected sum of rewards. Policy is something that maps from our state to our action or a distribution of our actions. And your expectation is stochastic because of the dynamics and the policy both being stochastic, right? And our goal has been to like maximize this expected sum of rewards. We did imitation learning, which doesn't actually maximize the expected sum of rewards. It does maximum likelihood given an expert, but it doesn't use rewards. It doesn't do this objective. We saw there were some issues with compounding error. It doesn't take expectation under policy, right? And so we're going to try and directly solve this objective. So I think we covered this, but you can have things be finite horizon or infinite horizon. Throughout this lecture, I'm largely going to stick to finite horizon, and I'm going to like shorthand it for the policy to be stationary. But if you want to do it properly, you can also do it. It just makes the notation a bit more complicated. So the objective here we're going to use has certain assumptions, right? So these assumptions are important because they like dictate why we're going to use this particular method. So the first assumption is that rewards are additive, right? Which means that what your goal is to optimize is the sum of rewards. It's not the product of rewards. It's not any other function of rewards. It's an assumption that rewards are additive. Right? The second thing that we're going to assume is that we have access to the dynamics for sampling purposes. So you can take actions in the environment, but you don't know the underlying functional form of the environment, right? Which means that you don't know the gradients. You can't reset it arbitrarily. It's not like a simulator where you have access to it. You have to obey the dynamics of the environment, as in you can like step through the world by taking actions, but you cannot take gradients through it, and you cannot like reset it as you'd like, right? The third assumption is that rewards are going to show up magically, right? So you're going to act in the environment, and some oracle is going to descend and tell you what the rewards are. For now, we're going to assume that rewards are going to come from somewhere. In some of the later lectures, we'll talk about like how do we build methods that can assign rewards and so on. Right? But for the sake of this formalism, rewards are going to appear every time you visited a state, but you don't know the functional form of the rewards. So you just get a number. So you're at this state, it gives you a number. At this state, it gives you a number, but you don't know the functional form of the rewards. Right? Which means that I like don't know a function that tells me what it is. I just have an oracle, let's say a human, labeling how good my reward is. So that's kind of what the assumptions of reinforcement learning are. The reason this is different from optimal control, which lots of you are familiar with, is for a couple of reasons. But the primary one really is the fact that the model is assumed to be unknown. Like in optimal control, you're going to assume that the model is known, and you're really trying to optimize this objective. Right? In reinforcement learning, you're going to assume that the model is not known. You can sample from it, but the model is not known. And there's other tiny differences, like you do min versus max, you do continuous time versus discrete time. But those are details. Like really the difference is whether the model is known or not known. Right? And if your model is known, then things like exploration, they matter for the sake of optimization, but they don't matter for the sake of figuring out what the model is. Right? Whereas if your thing is unknown, like in reinforcement learning, you have to explore the world to figure out what the model is to optimize it. Right? So things like exploration are bigger deals in reinforcement learning than they are in optimal control. They still matter, but they're different. Okay. So we just need to remember these assumptions. Like if you ever feel like you want to take gradients to the dynamics, remember you cannot. As I said, we cannot. And then the reason for that is not arbitrary, it's so that you can apply it to a broader class of systems. What's kind of interesting is even when people apply reinforcement learning in simulation, people use these assumptions in a system that doesn't have to have those assumptions, right? So for instance, you're like doing reinforcement learning in ISIC gym or something like that, or you're doing reinforcement learning in a differential simulator, like you don't need to obey these assumptions, right? So remember that these are the algorithms I'll talk about today, obey these assumptions. But if your simulator gives you access, if you have a different form of rewards that are differentiable, you should like use those assumptions where you can, right? And so like if you're doing reinforcement learning in simulation, you don't have to restrict yourself to these assumptions. Okay. So that's the connection between RL and optimal control. So the key premise of this class and a lot of what we'll talk about is how do we optimize this objective, maximize the expected sum of rewards under your policy phi theta. The easiest way to do it is gradient descent, which is what we'll talk about today. The second thing we're going to discuss is dynamic programming, which is what we'll talk about next week. And then the last way of doing it is something we call model-based optimization, which is saying you're going to try and learn a surrogate model of your environment and use that to do optimization, right? And so it's going to try and convert reinforcement learning more into an optimal control problem, right? And so those are the three techniques we'll largely cover. There's more techniques than that, but these are like the easiest ones. Yeah. Okay, but remember, all of them are essentially trying to solve that objective. There's just different approximations to solve it, which have different properties. Okay, let's start with the first, and we'll cover what the pros and cons are when we get to the end. But let's start with the first, which is going to be gradient descent. Yeah. Okay, so I mean, we all know what gradient descent is. The question is, why is gradient descent non-trivial for the reinforcement learning? Right? So gradient descent, to recap, is basically saying that if you have an objective, let's say on the x-axis you have theta, the y-axis you have your objective, right? You're going to try and follow the gradient in order to like find the peak of that objective, right? Or at least the local optima of that objective. And so essentially, we're just going to move the parameters in the direction of the gradient of the objective, and that's going to get us to the peak. And so the important thing that you need to have is you need to have access to, let's say your function was, f of theta, right? You need to have access to the gradient f of theta with respect to theta. And we're going to use that to move your parameters to the optima, right? Okay, so essentially, this is a graphic I stole off the internet, but it's kind of like showing that you take little incremental steps, and that you kind of follow the gradient is telling you which direction the objective gets better in, right? So the gradient is just telling you if I perturb the input, how does the output change? You follow the gradient, you do ascent to find the maximum, right? Now, gradient descent is not the only way to do ascent, right? It's like one of many optimization methods you could use. We can actually show that gradient descent is doing steepest ascent when you impose a Euclidean norm. And what that means is that you're going to like show that if you say that the parameters have to stay within a Euclidean ball of the current parameters, the direction that will improve the objective the most is going to be the direction of the gradient, but only under the Euclidean norm, which means that you're like, let's say you're at some theta. Let's say you're at some theta and you want to go to some theta prime, okay? And you're restricting your theta prime to be within a Euclidean ball of your theta, which means that like theta minus theta minus theta prime is going to be within some epsilon, right? You can show that under that constraint, gradient descent is steepest descent, right? It's telling you it's the direction that improves the objective the most. We'll derive that probably next class, but for now, just think of it the simplest way. You're just trying to improve your parameters. You're trying to say start from here, improve according to the gradient. When your gradient is 0, your parameters stay consistent, which means you've reached your optimum, right? And if you're maximizing ascent, minimizing descent, right?
What assumptions do you have in the code?
You just have the gradient. I guess you have the gradient, and it's you're not assuming that you get to a global optimum. So you're not assuming convexity. You're just saying get to a local optimum. Okay. So that's the basic idea of gradient descent, right? And so let's start by thinking about what gradient descent looks like for supervised learning. Okay? And then we'll show why it's not as simple for RL. So the supervised learning objective, like we covered, is basically saying try to maximize this thingy. Like this is essentially our f of theta, right? We're trying to maximize the log likelihood of A star being produced at S star for A stars and S stars sampled from your data set. Your data set's coming from an expert, right? Okay, so we're going to try and expand this out. And so we're going to say, I'm going to take the gradient of this objective. So I'm just going to do gradient descent. I'm going to treat this as f, and I'm going to do gradient descent. Okay. So the first thing I'm going to do is try and compute grad theta, right? And so if I take my expectation and I write it as an integral, right? So I have an expectation. Let's say the expert data set, let's say it is coming from some distribution P of S star, A star. Let's say that's your like expert distribution. We're going to say that this expectation can be written as the integral of log pi theta A star given S star multiplied by the likelihood P of S star A star times D of S star, D of A star integrated over all stars and A stars. Right? Now, as long as your functions are continuous, you can move this thing inside, right? And so in this case, the only thing that depends on theta is this guy, right? The only thing that your learner controls is log pi theta, right? So you're going to move it inside to get P of S star A star, grad theta log pi theta, right? And then you have this thingy, you can rewrite it as an expectation, as expectation S star A star coming from D, grad log pi theta. Right? So it's like a silly little derivation. But the important thing here is that I've taken the gradient of an expectation and I made it the expectation of a gradient. Right? Which means that I'm going to sample a bunch of S stars and A stars. I'm going to compute the gradient for each S star and A star, and then I'm going to average all the gradients. Like this is what we do in like mini batch gradient descent. You compute the gradient for each thing, and then you average all the gradients, and then you take the average gradient. And so the important thing was that this P of S star A star did not depend on theta. Only the log pi theta depended on theta. So you can move the gradient all the way in to the log pi theta. And so your gradient of expectation is expectation of gradient. Right? Does that make sense? So we just said supervised learning is expected log likelihood. You want to maximize it. You take the gradient of expectation is equal to expectation gradient. And the important thing is that this P of S star A star, which is essentially this expectation, does not depend on theta. Like your learner does not control your data distribution, so you can move it all the way inside, right? So whenever you have a gradient of an expectation and this expectation variable does not depend on theta, just move the theta all the way in. It doesn't matter. Right? When it does depend on theta, it becomes a bit more complicated. So the point here is that we have an expectation of gradient. And the reason an expectation of gradient is nice is because obviously I'm not going to integrate this over all possible states and actions. That's like infinitely many. So when you have an expectation of something, you can approximate it using samples, right? And so you can do what you call a Monte Carlo approximation, which is going to say, I'm going to like take n samples. Let's say I sampled AI, A1, S1, A2, S2, A3, S3, till like AN, SN. I'm going to compute an approximation to this expectation by like averaging together grad log by AI, given Si from I equal to 1 to n, right? And so what I've done here is I've taken an expectation, which is really an integral over infinitely many states in action. I converted that to an average over a finite number of samples that I can take, which is something I can compute in code, right? All I'm going to do is sample a bunch of S's and A's. I'm going to like each of them evaluate the gradient, average the gradient over all of them. That's going to be an approximation to my true gradient, right? So this is your true gradient. This is your approximate gradient. And as n tends to infinity, your true gradient, if your estimator is what you call unbiased, right, then your true gradient will approximate your sample gradient will approximate your true gradient, right? And so this thingy will get closer and closer to this thingy as n tends to infinity. Right? Okay, so I know I spent a long time on something that seems trivial, but the important part is that when the expectation does not depend on theta, move it all the way in. And you really want to get everything in the form of an expectation so you can estimate it as samples. Right? So if you cannot estimate things as samples, that's when you're in trouble. If I have to do integrals are bad, samples are good. Right? So anytime you have an integral, which is not an expectation, you're unhappy. Okay, everyone with me? Sweet. Okay, so now if I want to take the same approach to my problem of maximizing rewards in reinforcement learning, what's different about this objective, right? So let's kind of shorthand this objective a bit so it'll make our notation easier. I'm going to say that the likelihood of a policy is going to be p theta tau. Okay. I'm going to say the reward of a trajectory is going to be r tau for now. Okay. So r tau is just the sum of rewards in a trajectory. P theta tau is basically the likelihood of a trajectory, which, as we discussed at the start, is the likelihood of the initial state times the likelihood of the policy times the likelihood of the dynamics over and over and over and over. So we'll go into this in a second, but you can kind of think of this as the average reward of a policy is the expected likelihood of or is the integral of the likelihood of a trajectory times the reward of a trajectory over all trajectories, right? So this is just expectation p theta tau of r tau. Okay. So this is saying maximize the expected sum of rewards. You sample trajectories from pi theta in your environment. You then compute the sum of rewards of each of those trajectories. And then you say average them over all possible trajectories, weighted by the likelihood of each trajectory. Everyone follow that? Question? Okay. Yeah.
So what's the relationship between the reward objective and the most likely
Of the expert?
Yeah.
From imitation learning. So you can often like at a surface level, you can kind of think of like log pi e star as r. So you can kind of think of like if you're thinking of the reverse scale objective, right? So you're going to do something like this, right? And then if you like think of this, if you think of log pi e star as r, then you can kind of write this as expectation pi theta of log pi e star, or log pi e, sorry, minus expectation pi theta, log pi theta, minus on this whole thing, right? And so if you think of this as like r, right? Or actually you want to think of this as like sum of r along the future trajectory. And this you can think of as entropy. Like then you can show that the reverse scale objective is kind of like maximizing the sum of rewards plus entropy. And so I think it's I don't want to get too much into it without context. We'll have a whole lecture on connecting these two things, but the easiest way to think about it is log pi e is kind of equal to like the sum of rewards in the future, right? And so we can show that those are exactly equivalent, but we'll do that in like 2 weeks or so. Make sense? Kind of like intuitively, you can kind of think of it as like the higher the future reward for a particular action, the higher its likelihood is going to be under the expert. And so you can kind of think of log pi star as your reward. Okay. So that's going to be my objective, expectation pi theta tau of r tau. Now, what's going to make it, why can't I just do gradient descent on it? Like, what makes it hard? Theta is in the expectation. Perfect. So theta is in the expectation. And so the issue is that we have objective that looks kind of like this, which is saying you're going to take the gradient of an expectation where the gradient is with respect to theta, and theta is inside the thing you're taking expectation with respect to, right? Whereas if you look at supervised learning, it looks more like this, where you're saying you're going to take expectation with respect to some g, which does not depend on theta. And think inside your expectation is what depends on theta, right? So at supervised learning, we said, okay, we're just going to move the theta all the way in. We're nice and happy about it. But if you're going to take the gradient of something where the expectation variable itself depends on theta, it's not as simple, right? Because we will cover that in a second. But the difference between these two things is one of them has expectation depending on theta. The other one has only the thing you're taking the expectation of depending on theta, right? So you ever want to think about the difference between supervised learning and reinforcement learning? This is more supervised learning. That is more reinforcement. So theta has to control the data distribution in RL. Theta does not control the data distribution in supervised learning. Okay. Okay, so why is this problematic, right? So let's kind of like whiteboard this out. Yeah. Kind of whiteboard this out. So if I think about this, let's look at this objective right here. Okay. If I look at expectation, the gradient of expectation, x sample from p theta of x of f of x, right? I can write this as the integral p theta x f of x dx, gradient with respect to theta, right? I just expanded the expectation. And so now I can again move my gradient inside, but notice that f doesn't depend on theta here, p depends on theta, right? So I can write this as integral grad theta p theta x f of x dx. And this is, I mean, this is a perfectly valid expression. The problem is that this is not an expectation anymore, right? So like an expectation, right? An expectation of some p of x f of x is something which is an integral of a probability distribution multiplied by a function dx, right? Sorry. So whenever you have an expectation, it has to be a probability distribution multiplied by a function integrated over a variable. This thing is not an expectation, right? Because you actually have the gradient of p, not p. And so this by itself is not an expectation, and integrals are bad, expectations are good. And so we don't have something that we can compute with samples, which is why this is hard. Right? Does that make sense? So the difference here was that we the thing that we took the gradient with respect to left the distribution untouched. And because the distribution was untouched, you could make the gradient of an expectation into the expectation of a gradient. So you're good. You can compute it with samples. Here, what we're going to say is that because the theta depends on theta, you're going to have something that is not an expectation. Now, non-expectation means you cannot compute it with samples. And so this thing is an integral, but it's not an expectation. Or not yet. Okay, does everyone follow that? Good. Sweet. So what we're going to do next is we're going to try and like make it into an expectation. All right. So before I give you the answer, what are folks' ideas on trying to make that problem into an expectation? Like, so the issue here is going to be, let's see, we have this objective. You have its gradient, and that gradient is going to be not an expectation, right? So let's cover this in a little bit of detail before I pause. Basically, that objective is saying maximize the expected sum of rewards under your policy and your dynamics. We're going to rewrite that with a shorthand which says, take the integral of the likelihood of a trajectory times the reward of a trajectory over all trajectories, right? And then you're going to say, I'm going to take the gradient of it. The gradient goes inside. The gradient hits p theta tau, not r tau, because p theta is the thing that depends on theta. Now, this thing is not an expectation. That's the problem. Okay, so it's basically the same thing as we did earlier. I just instantiated it in RL land. Okay? So like the problem here is that that's our objective. We took the gradient. The gradient is not an expectation. Now, how do I make it an expectation? You could make the reward a distribution, but you kind of like one way to think about this is that p theta tau is the distribution of trajectories that you get from running things in the environment. And so you kind of want to have it be an expectation over over p theta tau, because that's kind of like an average over trying different things in the environment. So yes, you could certainly try to make this a distribution, but that's maybe like different than having a distribution over things you executed in the environment. But that's good. Other ideas? How else could we make this? Yeah.
I don't have an answer to that
Okay.
question.
Yeah.
Is it valid to take the gradient of p theta? Like, what does it mean to take the gradient of p theta?
It means that so p theta is a probability, right? So it's saying like what, and so probability is a scalar. And so it's telling you like, if I move my theta, right, how does it move the probability? So it's kind of like if I had like a neural net, which outputs the mean and covariance of a policy or probability distribution. If I change my parameters in my neural net, how does it affect the likelihoods of the policy, right? And so you can just think of it as dp theta tau d theta. Integration by parts, you could certainly do it. It's just a huge pain. But we'll have a trick that'll make it easier. You could do integration by parts, yeah. So let me maybe give us a little hint on this trick. All we're going to do is we're going to multiply and divide by p theta tau. Okay. Yeah. That's right. That's right. Yeah. Yeah. That's right. Okay. Yeah. Yeah, we're going to convert to the gradient of the log. So exactly what we're going to do is we're going to multiply and divide by p theta tau. Right. This just keeps everything the same. And then we're going to do a little bit of grouping. And so we're going to treat this as one term. We're going to keep this because we really want to do an expectation with respect to p theta tau. Right. So what we're going to have is we're going to have an integral of p theta tau of grad theta p theta tau divided by p theta tau times r tau times d tau. Yeah. And so all we did is we multiplied it, divided, and we grouped these terms together. Now, as we just said, essentially, if you look at this term and you use the chain rule, if you have like grad theta log p theta tau, right? You can show that by chain rule, this is going to be 1 over p theta tau into grad theta p theta tau. Right? That's just by the chain rule of calculus. So you're going to say the gradient of the log is 1 over the value times the gradient of the thing inside. Right? So you're going to say, okay, this, I multiplied and divided, I grouped these terms together. Then I noticed that grad p by p is just grad log, right? And so all I'm going to do now is I'm going to like notice that I'm going to notice that these two terms grouped together are essentially grad log. And so I can rewrite this thing as p theta tau grad theta log p theta tau times r tau d tau. Right? So all we did is multiplied and divided and use the chain rule. Yeah. Okay. So this is a pretty general trick. Like it doesn't have to just be for RL. Like any objective which looks kind of like that thing on the top, right? So anything where you like can sample, and the thing you're sampling with respect to depends on theta, you can kind of use the same trick. Okay. So we wrote this as integral p theta tau grad theta log p theta tau r tau. Nice thing about this is it's an expectation again, right? So we said an expectation was some p of x, f of x, dx. In our case, this is p of x, this thing is f of x, this is dx, right? So it's gone back to being an expectation, which is nice, because then I can rewrite this as the expectation p theta tau of grad theta log p theta tau r tau, right? And now integrals are bad, expectations are good. So we have something we can compute with samples, right? And so notice that p theta tau is the distribution of trajectories in your environment. you can compute this objective by just running trajectories in your environment. It's easy to sample, right? And because you know p theta tau, or we'll talk about that in a second, because you know p theta tau, you can actually compute this thing easily, and the reward is given to you, right? And so everything is in terms of things you know how to compute. And so that's what makes this nice, in that you've taken this gradient that was not an expectation, and you've converted it into an expectation. You're never requiring us to like solve an integral. You're just going to do it with sample. Yeah. Okay. So okay, we have 8 minutes. I think one thing that would be useful is to like concretize this a little bit. This is still in terms of like abstract trajectories and so on. Let's like concretize it in terms of states and actions and like something we can actually implement. Okay. So this is often called the reinforced trick or the policy gradient trick. But what I want to do next is kind of like take these abstract entities, p theta tau, r tau, and I want to instantiate them in terms of like states and actions and like concrete things, not abstract things. So what we're going to do, the first thing we're going to do is we're going to try and, expand out p theta tau. So tau is a trajectory, and so trajectory is a sequence of states, action states, action states, action. And so p theta tau is going to be the likelihood that a trajectory occurs under your dynamics and under your policy, which means that it's going to be the likelihood of your first state times the likelihood of, you can write this as P of S naught times the likelihood that the policy took action A naught at S naught times the likelihood that you actually transition to S1 given S naught and A naught, times pi of A1 given S1, P of S2 given S1, A1, so on, right? And so the point here is that you can write this as the product of the initial state distribution times the policy times the dynamics times the policy times the dynamics times the policy times the dynamics. So you just repeat it over time. And so this, given a trajectory, this is how likely it was that I sampled the trajectory, right? So intuitively, you can think of things that like, if I took an action that was really high likelihood, that trajectory would likely be high likelihood. If I sampled something that was really low likelihood, that trajectory would probably be low likelihood. But the likelihood of an entire trajectory is essentially a product of the initial state likelihood times the dynamics likelihood times the policy likelihood. Right? You can just kind of like, because it's Markovian, you can break it up step by step by step. You can think of it as this thing times 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 this thing. Right? You're just like breaking it up step by step and saying that the likelihood of a trajectory is the likelihood of these individual components. Right? And so we defined the dynamics at the start of the class. It's the likelihood that I transition to ST plus 1 given ST and AT. We've been talking about a policy. Policy is pi theta. It's the likelihood that your learner takes AT given ST, right? And you have some initial state distribution. Make sense? Questions? Okay. So that's just what the definition of p theta tau is, right? It's like, what is the likelihood that you took a trajectory? We're now going to stick it into our objective, right? So our objective had this grad log p theta tau term, right? So if you remember, our objective had this grad log p theta tau term down there. And so what we want to do is we want to like write out what grad log p theta tau is going to be, right? So we know that log of a bunch of product of terms is just the sum of log of those terms, right? Log product is sum log. And so you can say that this log p theta tau is log probability of the initial state plus log of the dynamics plus log of the policy, log of the dynamics, log of the policy, repeat, repeat, repeat. Yeah. Yes, using the Markov assumption. Right. So the place that I use the Markov assumption is saying that your policy only depends on your current state, and your dynamics only depends on your current state. So here we're saying that the log p theta tau is log of your initial state plus log of your dynamics plus log of your policy repeated over all time steps, right? Now, why is this cool? Because if you take the gradient of this, right, you'll see that you can separate the gradient of sum of a bunch of terms is just sum of the gradient of each of those terms, right? Which means that you have gradient of this plus gradient of this plus gradient of that. But only one of those terms actually depends on theta, which means that these two things just are zero, right? Your dynamics don't depend on theta, The dynamics are just the environment. It doesn't matter what your learner is. The dynamics are the dynamics. And your initial state doesn't depend on theta. Your policy cannot control the initial state. Your policy cannot control the dynamics. Your policy can just control what actions it takes in the world, right? Which means that your grad log p theta tau just becomes the sum of grad log policy, right? So the only thing that depends on theta here is the last term, not the first two terms. And this is why you call it model-free reinforcement learning, because you do not need to know the model. Like the gradient of the model just cancels out, right? So while model-based reinforcement learning will try to take gradients through this, in model-free reinforcement learning, the grad log p theta tau does not depend on this. It does not depend on this. It's just grad log of your policy, not of your model. Right? So that's what makes this nice and model-free. Okay, so let's put that back together. It means that grad log theta tau is the sum of grad log pi theta at given st. So let's say I sampled a trajectory. For each of the states in that trajectory and actions in that trajectory, I compute grad log pi theta, where pi theta is my policy. We'll instantiate that concretely x class problem. You can compute this because you fully choose what pi theta is. You compute the sum of that, and that gives you grad log p theta tau. And so you can now stick this into your objective. So you started with, your objective, which was grad log p theta tau times r tau. The first thing we did was we said that, hey, r tau is just the sum of rewards in a trajectory. The second thing we're going to do is we're going to expand out grad log p theta tau, just as we did right now. So you're going to say it's the sum of grad log pi's times the sum of rewards. And notice that you're sampling trajectories according to your policy and according to the dynamics, but you're never taking the gradient of the dynamics. You just need the gradient of the policy, right? And so the gradient of the policy becomes, when you have this expectation, you can approximate it with samples as following. You take n different trajectory samples. For each of those samples, you sum up the grad log pi's, and you weight each of those grad log pi's by the sum of rewards in that trajectory, right? So I did a bad job bracketing these things, but it's going to be, you can kind of think of it as like, this is telling us what is the likelihood of actions in a trajectory. This is telling us what the sum of rewards is. And we're going to essentially sample a bunch of trajectories, compute the grad log, and multiply it by sum of rewards. And that's going to be your policy gradient. I know I'm like almost out of time, but I want to communicate like a little bit of intuition. So the way you can kind of think about this is that you're going to sample a bunch of trajectories. Okay, and then you're going to like take the trajectories, weight them by their sum of rewards. And you're going to increase the likelihood of the actions in the high reward trajectories and decrease the action of the likelihood in the low reward trajectory. So it's like literally trial and error. You're going to try a bunch of stuff. You're going to increase the likelihood of the stuff that was low reward, decrease the likelihood of the stuff that was, or other way around, increase the likelihood of the stuff that was high reward and decrease the likelihood of the stuff that was low reward, right? And so essentially you can kind of think of this as how much you want to increase the likelihood, you weight it by the sum of rewards. So the stuff that is higher rewards gets weighted more, gets weighted higher. The stuff that is low rewards gets pushed down, right? And so policy gradient is just saying, sample a bunch of stuff. Stuff that is high reward goes up, stuff that is low reward goes down. That's it, right? Okay, I think that's a good spot to end. Maybe we'll continue on Wednesday.